Okay, we were studying traveling waves in class, and we've been doing examples where I show you the wave shape, and then I ask you to make a plot of the speed of the individual elements of the wavers that make up the wave. And so several of you have asked if I would do another example or two that you could look at. So I'm going to put them here on a video for you to study how I do this to go along with the examples that we did in class and the examples that we did on homework. So to do this, we got to have a wave shape. So let's imagine we have the following traveling wave shape. So whenever I draw waves, the very first thing I do is I draw the equilibrium line. When I give you a wave shape, say on homework or on exams or something like that, that equilibrium line will certainly be there, or I try to remember to put it there. But when you're doing calculations and drawings yourself, it's helpful to put the equilibrium line down because that's what we're measuring everything against. So let's imagine the following wave shape. So let's imagine we have some string with a pulse that is traveling along it, and let's imagine that I have a string that has the following shape. So it's initially flat, it has some diagonal up, it has a flat top, and then it has some diagonal down, and then it is flat again at the equilibrium length. So it has this kind of trapezoidal shape. Okay? And let's imagine that that wave is traveling in this direction. Okay? So that means it's maintaining this pulse shape, but a little while ago this whole pulse shape was over here, and sometime in the future this whole pulse shape is going to be over here. And what we want to do is we want to describe what is the speed of each of the individual little elements that make up this string in this pulse, and what the speed of those wavers has to do in order for the pulse to propagate in the direction indicated here. Now, to do this, there's a variety of ways you can do it. I think of this as being frames in a movie. So you could imagine drawing the frame before this one or the frame after this one that shows this pulse shape in a different location. You could draw those shapes below or draw those shapes above. But I often find it convenient to draw the next shape or the previous shape directly on top of the frame that I already have here. So let me do that. Let me do it in a different color. So this wave pulse is going to be traveling to the right here. So that means this whole shape is going to be exactly where it is, but it's going to be shifted over just a little bit. Now, I don't want to shift it tremendously far because I'm trying to describe what is the speed in the wave pulse right now at this moment. And if I shift it way over here, it's going to take some time for this pulse to get over to here. So that won't be accurate. But I do need to shift it a little bit just to get at the basic physics that I'm after. So I'm just going to choose some small but arbitrary distance to draw the new pulse, and it will look like the following if I just were to take a video of this traveling pulse and wait for the next frame. Okay, so you see there that I've drawn exactly the same pulse, but the pulse shape has shifted in the direction that the wave is moving just a little bit. Okay, now I want to plot what is the speed of each of the individual wavers in this string that will move me from the original purple pulse into the red pulse, which is the purple pulse a little bit into the future. And what I'm going to do is I'm going to plot the speed of each of those individual wavers. So what I'm going to do is I'm going to make a plot down below this where the vertical axis of the plot is the speed of the waver, is the speed of the waver, v, okay? And I'm going to draw a dotted line for the horizontal axis, okay? So that is speed 0. And so above that axis, the wavers have positive speed, or that is to say they are moving up. And if I'm below this line, then the wavers have negative speed, or they are moving down. Okay, so these are elements on a string, and as we've said in class, a string is a transverse wave. So if I were to imagine any little element on the string, all it does is it moves up and down, and the combination of all the elements of the string moving up and down give you the pulse shape as it's moving. Okay, so the next thing I do is I'm going to look at the two pulses that I've drawn, and I'm going to draw an arrow. Okay, in fact, I'm going to draw a series of arrows. I'm going to draw them from my original purple wave to the red wave. And what those arrows are going to represent is the direction that an individual waver along the purple line would have to move in order to become the red line. That is to say, the direction this waver has to move for the pulse that's drawn in purple to move and become the pulse that's drawn in red. Okay, so let's look at this waver right here where I've drawn a dot. Okay, so that waver is currently on the purple pulse, but in order to be a part of the red pulse, it has to move down. So I'm going to draw a little arrow down. Okay, and so that arrow goes from the purple to the red. Similarly, this one has to move down, and it goes from the purple to the red. Okay, let's think about that waver right there. Okay, so that waver is in the same position on both the purple and the red, so it doesn't have to go anywhere. Same here. Okay, but this waver, which is on the purple pulse, it was low, and in order to get to be the red pulse, it has to move up. So I'm going to draw the wavers there representing the pulses moving up. Okay? Now, you see here a little bit of the danger in this method, which is, I've shifted the red pulse pretty far over, and so there's this kind of confusing region where the waves are not overlapping. Okay, so we're going to make some guesses as to what that should look like, but really what we're interested in is the pulses when they are just barely shifted from each other, and so those regions where there's this confusing overlap are very small and very not very large and important. Okay, if I were to draw this exactly the way that I'm interested in, there would be the original pulse shape, and then the next pulse shape would be shifted just the tiniest amount over, and so I'd be drawing little arrows just between them like this, but I've exaggerated it here for the purposes of our demonstration. Okay, so now I'm going to take these arrows and I'm going to use them to plot the speed down here. Okay, so over here in this region of the wave, my wavers aren't moving at all, and so they have 0 speed. And then when I get to here on this upslope, the wavers have arrows pointing down. That means they have negative speed, and they're all roughly the same height along here. So that means at the point where I get to the edge of the wave, my speed goes to some negative value that's the same for this entire upslope of the wave. Okay, so you can imagine drawing all of those arrows, and they'd all be roughly the same length. Okay, and so that makes this little negative box length. Then this whole region along the flat here, everything is exactly the same place. The wavers aren't actually moving. So that corresponds to 0 until I get to this point. And then here, all the wavers are moving up. In order to go from this slope on the purple to the red, they have to have some positive speed. And again, all of those arrows are roughly the same height. And if those slopes are the same on the left and the right, they'll look exactly the same as my negative one there. And so I have this region here that looks like this. That's the width of the diagonal slope. And then I go back to 0 for this part of the wave. Okay? So that is my speed plot that corresponds to this pulse shape moving from the left to the right. Okay? I hope that helps some. We'll do another example sometime. Good luck.